towards the end, which will scare people. Is anyone here able to go 5 or 10 minutes late, or do people have things to go to immediately afterwards?
Some of us do have something straight after, a few of us do have something straight after.
So what I'll do is I'll try and I'll wrap up the main material within time, and if there are people who want to stay for maybe 5 or 10 minutes extra material, I'll do that at the end. And again, apologies for that.
I think there's a lecture immediately after this one.
Yeah, play informatics.
Yeah.
No, try to come in this room.
Ah, yes.
It's all going to happen within time. I'll just cut some of the material for you. Yeah. Okay. So, okay. At least this thing is very low tech. This cannot go wrong. Or exactly this. Okay. So the whole of the last lecture was going to go through various value-based reinforcement learning methods. And what I'd argued in that lecture was that if you wanted to scale up to interesting problems where the MDP is large and you can't represent the value function of individual states, that we need to use some kind of function approximation. So in the last lecture we looked at methods that were able to approximate the value function using some parameter vector theta. So we either looked at parameterizing this state value function using v theta and estimating this v pi, or using parameters to estimate the action value function q theta. This is a very widely used approach, but there is a major alternative, which we'll look at in this lecture. So what we did last time in the last lecture was we basically formed our action value function, and then we used this action value function to sort of generate this policy from the value function. So for example, using epsilon greedy policy improvement. But the alternative, which we'll look at today, is to directly parameterize the policy. So instead of using a value function at all, why not work directly in policy space? If at the end of the day we're after a policy, we want to represent that policy as probability distribution over actions conditioned on states with some parameter vectors theta that we're going to adjust. So for example, this might be in a continuous action space, this might be a Gaussian policy. And we're just going to adjust the mean and the variance of this Gaussian to be just the right shape to take actions that we really want to take in the states that we care about. Okay. And again, we'll focus on model-free reinforcement learning. So there are model-based approaches to policy gradient. We're not going to deal with those this lecture, but you should be aware that they're out there. So what we're going to do is sort of go back to this. This is roughly the picture we had in the very first lecture, the introduction to reinforcement learning. Which sort of gives this taxonomy. And we're going to be looking at this part of the taxonomy today. So this is all model-free now. So there's no model, but we're going to consider basically, last time we looked at this value-based space here, where we just have a value function, and the policy was implicit. There was no explicit representation of the policy. So this taxonomy, remember, is based on what the agent actually stores in its memory. So if the agent stores a value function in its memory, if it creates this value function explicitly, we say that it's value-based. And today what we're going to look at are these policy-based methods, where to begin with there'll be no value function, but there'll be this explicit policy that's stored in memory. The parameters of this policy are explicitly updated. And that's this guy over here. We have some policy stored in memory, and these are called policy-based methods. But in between, there's this area where both of these are stored in memory, and that's what we'll do in sort of last part of the lecture today. We'll look at actor-critic methods, where we both represent and learn the value function and the policy. And we'll see that these actually can gain the best of both worlds. So we can gain the sort of power of working directly in policy space with some of the learning efficiency that we gain from value-based methods. Okay. So why should we care about policy-based reinforcement learning? Well, there's various reasons that you might hear about. Here are some of the most common ones. So policy-based reinforcement learning. One of the advantages is this tends, because we're working directly in policy space, if you find a good policy, you know you've got a good policy. So for example, if you do gradient descent through policy space, you'll always find a local optimum in policy space. So it has better convergence properties. Remember last lecture we saw there are certain cases where value-based reinforcement learning with function approximation can be problematic. Whereas for policy-based, even if you have some complicated nonlinear policy representation, it will always work and find some reasonable policy. It can also work with continuous action spaces. For example, when I mentioned you could represent your policy by a Gaussian policy, this is something which can work in continuous action spaces or in high-dimensional action spaces. Whereas value-based methods, it can be harder to generalize to continue. It's still possible, but it's these methods, policy-based reinforcement learning tends to be the method of choice when you move to continuous action spaces or high-dimensional action spaces. And another advantage, which I'll give an illustration on in just a second, is that we can learn stochastic policies. So rather than just the deterministic policies that emerge if you choose like greedy policy improvement, if you have a value function, you pick actions that maximize your value, that's always going to give you a deterministic policy. But the disadvantages are that this just converges to a local rather than a global optimum, because there's some complicated space in policy space. So we typically give up on global convergence guarantees, not always, but typically. And what we'll see is, to begin with, when we use the pure policy-based methods, this can be a little bit high variance, these estimators. So we'll have to work a bit harder to regain the efficiency that we had in the value-based RL. And that's where the active-critic methods come in. Okay, so let's get a couple of motivating examples. So I guess everyone familiar here is familiar with this game. There's various names: rock, paper, scissors, Rochambeau. So anyone not know this game? Okay, good. So just someone shout out, what's the optimal way to play rock, paper, scissors? Does anyone know?
We'll wait to see first what the other guy got.
Okay. So there's a certain sense of optimality, which is known as the Nash equilibrium in game theory, which basically says a policy where you wouldn't change your policy. Basically, both players would be unhappy to move away from what they've got. So it's some sort of local equilibrium policy. And in rock, paper, scissors, if you just keep playing this game against someone, you can imagine if you don't know anything about your opponent, anything you do where you pick, say, one action deterministically, you will always get beaten because your opponent will figure out, well, I just keep playing rock, so then they'll learn to play paper all the time. So deterministic policies are very naive in games like this. And so what you really want to do is to be stochastic. You need to randomize to make sure that you're not going to be exploited by your opponent. And in this particular case, the optimal policy is just to play 1/3, 1/3, 1/3 as the equilibrium policy. That's the only thing. If you play that, you can't be exploited. So if you play that, if both players are playing that, neither of them would choose to move away from that because they could be exploited, essentially. So there's a sense in which this is optimal. So this is one example where it becomes important to have a stochastic policy, and the value-based methods we looked at would be inadequate for finding this solution. They simply would just pick greedily one of the three choices, and that can't be good. Okay, here's another example. So this one required game theory. This one required a multi-agent setting for that to be true. So here's a single-agent setting, much more familiar to the kind of thing we've been looking at before. Very simple grid world, okay? You don't want to go here, it looks bad, right? Don't want to go there, that looks good, like lots of money, okay? Now the problem with this grid world is that it's aliased. What do I mean by that? I mean that the agent can't tell the difference between this state and this state. It doesn't know, when it's in here, it thinks it could be either here or here. It can't tell the difference between them. So one way, without changing the setup that we were looking at last lecture, one way that we can get this aliasing is to just consider features. So we're going to do value function approximation, but we're going to use features which just have this following form, where the features basically say whether there's a wall to the north or south, and whether, so the features of the state are going to be things like, is there a wall to the north, is there a wall to the east, is there a wall to the south, is there a wall to the west? So there'll be like there's 4 different binary features in the feature vector. But we're also going to consider features of the state and action space, like we did last time, to estimate our action value. So we're going to say things like, have a feature of something like, is there a wall to the north when I'm moving to the east? And if you try to represent, so what we're going to look at is basically trying to do this either in a value-based way or in a policy-based way, just to get some intuition. So if we were doing this in a value-based way, like we did last lecture, what did we do? Well, we tried to represent the action value function using these features. So you basically try to say, how good is it to be in a state where there's a wall to the north? How good is it to be in a state where there's a wall to the west? Whereas what we're going to do today is we're going to do something more like parameterize the policy directly. So we're going to say, if there's a wall to the north, what's the probability that we move east? Something like that. Okay, so what happens if we move deterministically? So let me ask you this question first of all. What's the right thing to do here? What's the optimal policy here? Given that you have aliasing, what's the best that you can do in this scenario?
Keep moving horizontally until you reach a wall, and then you know where you are.
Okay, so what you're doing is something called, you're using history to disambiguate the aliasing. So you can do that, but that's kind of cheating in that what we're doing is we're only making our decisions based on the features at hand. So you you can't remember whether you've seen a wall or not before. So let's look at this. So if we're moving deterministically, so if in each given state, given our representation, we're just picking based on whether there's a wall immediately now to the northeast, south, or west of us, if we're picking to go kind of northeast, south, or west, then this is the best we can do. We can either move west in both of these grey states, or we can move east in both of these grey states. So, you know, what this really means is that, okay, if we're on this side, we'll do okay. You know, we start here maybe, and we move to here, we move west, we move down, we get the gold. But if we're over here, we're just going to move backwards and forwards forever, and we will never get the gold. Okay, this isn't a very successful policy. The problem is that when we use value-based reinforcement learning, we're having to represent the value function just in terms of those features which are immediately in front of us. We're taking account of the aliasing, and we're being greedy with respect to those, so we're learning something deterministic. And even if we do epsilon greedy, we're still close to deterministic. All we're going to do is, with some small probability, we'll move away from that, so we still do quite poorly. And we'll traverse this corridor for a long time if we happen to be stuck on this side. In contrast, if you're moving stochastically, well, we can choose this other policy. We can say, okay, if you're in one of the grey states, then either move east or west, 50-50. And now what's going to happen? Well, no matter where you start, either side, you're just going to move backwards and forwards maybe once or twice, but very quickly you'll end up in this state here, and you'll end up moving down, and you will always get the gold in quite a short amount of time. So in this particular example, a stochastic policy can do much better than any deterministic policy. That's the point of this example. So when you have aliasing, and when you have function approximation, it's possible to do much better using a stochastic policy. In other words, if the agent only has a small amount of resource to represent in its memory, to represent either its value function or its policy, it can actually do better using those resources to directly represent a stochastic policy than a deterministic policy. So that's just some motivation for policy basis. So we've got these ideas that you might want to have a stochastic policy, either for game theoretical reason or because of this aliasing issue. They're better convergence properties, they're very robust, and they can be quite simple and straightforward to understand and interpret and use. Okay, so how do we actually formalize this? So we're going to come up with some objective function. So what's the objective function going to be? So we're going to do something like greater than %, and we want to sort of change our policy so as to make our get more reward in some sense. But how do we formalize that objective? Well, we need to be able to measure the quality of a policy. So given parameters theta, we need to know, well, how good is policy pi theta? And there are three different ways that we could do that. There are many ways, but here's three ways that we could do that. In an episodic environment, we could just use the start value. So there's some start state S1, and we could just say, okay, what we actually care about, the objective we're going to use is the value function of that start state. So if we're doing well from the start state, then we're happy with our policy. If there's a policy which from the start state ends up getting us a lot of reward, well, we're pleased with that policy. This makes sense in episodic environments where there's always some start and then you run until the end and then you finish, and all you just care about is how much reward you get from that episode. And so this basically kind of encapsulates that idea. This is just the value function, the expected return you get when starting in your state S1. But if we're in a continuing environment, this isn't really appropriate. There's no real sense of a start state anymore because you just keep going and going forever. This is something like an ergodic Markov decision process, if you're familiar with that. So what we can do instead is one of two things. We can either use the average value, which basically says, let's just look, for every state that we reach, let's consider the value function from that state. And we want to pick states in a way that just maximizes the average value of all the states that we reach under our policy. And as our policy moves around, we just want to make sure that we're continuing to get good value. And it turns out that this is actually proportional to this objective, which is the average reward per time step. So this one basically says, so this D is basically the probability that you're in a particular state under some policy. This is the stationary distribution. This is how likely you are to end up in state S, or just averaging over all the states that you could reach, multiplied by either the value of it here or the reward that you get. So here we're averaging over all states you might be in, all actions you might take under your policy, and the reward that you'll get from that state and that action. So it's the average reward per time step. So how much reward you'll get, you just keep moving around this policy per time step. Okay. And it turns out that everything we're going to say today is essentially the same for all three of these. So one of the nice properties of these policy gradient algorithms is that the theory applies to all of these. You don't need to worry, kind of, in a sense, which one of those you're dealing with.
So,
Yeah.
that's like the long-term visibility. So if you keep moving around it, that's a proportion of time you're going to spend in state S.
Yes.
If you keep wandering around, it's
Yeah.
environment 4.
Exactly. If you keep going forever, so in continuing environments we talk about something called a stationary distribution, which doesn't always exist, but yeah. So, but if you basically have the property that you continue to visit all states, so you have some noise in your environment or something like that, then basically this is the probability that you actually the long-term probability, how frequently you'll end up visiting that state compared to any other state. Okay, so now all we want to do is something, we're going to reduce reinforcement learning to a straight optimization problem. Okay, so policy-based reinforcement learning just means optimize that objective function we just looked at. So we want to find the parameter vector theta for our policy that maximizes this objective for one of those three objectives. So there's various ways you can do that. You can do it in gradient-free ways. So hill climbing, just at every step move to some better parameters. You can use these sorts of shape-based methods, simplex or amoeba or nil-to-mead, which basically mean that you take something like a triangle and then change one of the vertices, flop this shape over and over and over until you make progress up. It's a bit like hill climbing, but you're moving the whole shape at once and reevaluating the vertices of this thing. You can use genetic algorithms, genetically motivated optimization method. So these are gradient-free methods that just sort of blindly maximize J theta. And in general, you can do better if you have the gradient. You can typically do better in optimization problems by exploiting that gradient. So methods which do this are things like, I guess I should say, gradient ascent, and trying to maximize J theta, conjugate gradient, Newton or quasi-Newton methods. Okay, so if you have the gradient, you can use it. We're going to focus on the simplest case of this in this class, which is basically gradient ascent methods that use the gradient, climb in the direction of the gradient so as to maximize this J theta. And of course, once you have a gradient ascent method, it's typically possible to extend it in these ways, and people have done that. But again, in RL, we tend to focus first on the simpler methods, just because there's other complexities to worry about. Okay. So, and we're also going to look at methods that exploit sequential structure. And by that, I mean, if you think of something like a genetic algorithm or a hill climbing method, you have to run a complete episode to get one data point of how well the agent did in that episode. And then you get some example of what your J theta was, and given that example, you're then able to take a step. So it's a very expensive method. It doesn't exploit any of the sequential path that leads to the particular result of how much of the return you got is thrown away in those methods. And we're going to eventually look at methods that exploit sequential structure, just as we did with the value-based methods, where we used the Markov property to develop the Bellman equations, which led to methods like temporal difference learning. We were able to exploit that sequential structure. We'd like to do the same in the policy-based setting. Okay, so we're going to go through three classes of gradient ascent methods, starting with the simplest possible version and moving on to Monte Carlo methods and active critic methods. I think we'll have time for examples of all of these, and then what I'll do is there's some details at the end of this that I'll skip. Okay, so policy gradient. So we've got our objective function, J theta, which could be one of our three objective functions. And we're just going to search now for a local maximum. So we've got some surface, this sort of height of this surface represents our J theta. This is like a two-dimensional parameter space as an example here. This is like a contour plot of the same thing. Actually, it doesn't quite match this one, but anyway. And basically, what we're trying to do is adjust the parameters in the direction of the gradient. So we're just going to walk up the hill of this thing. Or up here, we're basically following the direction of the gradient at each step until we eventually will reach, just by following that gradient, a local optimum. And here, again, we're going to follow this policy gradient, where here, policy gradient now is this vector of partial derivatives of how our objective function changes in each of these directions. So how it changes with respect to parameter 1, all the way up to how it changes with respect to parameter n. And that's going to give us our direction of change. So at each step, we're going to adjust our parameters a little bit in the direction of that gradient. Okay. So the simplest method for gradient ascent is finite differences. And it's a very naive method. You may well be familiar with this already. And the idea is just to evaluate this policy gradient numerically. So all we're going to do is we're going to come up with a numerical estimate of each of these components. And the way we're going to do that is just perturb one of these components at a time and evaluate the policy by basically changing theta for just one of these components at a time. So basically taking a little step in this dimension and then a little step in this dimension and seeing how much that changes the policy. So for each dimension, what we're going to do is we're going to perturb it. So we're going to estimate this partial derivative by taking our theta, adding a little bit in just that dimension only. So this is a unit vector, just a 1 in that particular dimension, and looking at the difference that makes to the value. And that gives us an estimate of the partial derivative in that direction. So this is simple. We can basically just try it. We can say, okay, let's change parameter 1, see what happens to our policy. Change parameter 2, see what happens to our policy. Put them together, you get an estimate of the gradient. Move the parameters uphill in the direction of that gradient and repeat. So simple, effective. Problem is, it's a little bit slow. If you do this naively, it takes n evaluations. So there are n parameters. It will take n evaluations to compute a single policy gradient in n dimensions. You can do better. There are methods that use regression to estimate this more efficiently. But still, if you don't know the analytic gradient, you end up with some inefficiency. But it can nevertheless be effective. And it works for arbitrary policies, even if your policy is not differentiable. So you could have some crazy policy with step functions in it, and this idea would still work. Okay, so I just wanted to show you, just for fun, a couple of videos. So this is an example of a very successful application where people basically used policy gradient reinforcement learning using finite differences to train an IBO to walk better. So it turns out an IBO has something like 23 different parameters in its walk gait, and it's possible to optimize those parameters to come up with a faster walk. And the main motivation for this is a game called RoboCup Soccer, where you basically have a bunch of IBOs in this particular league, a bunch of IBOs playing against another bunch of IBOs, these sorts of robot dogs. And it turns out that because they're so bad, actually, at playing the actual game of soccer, the only thing that matters is how fast they walk. And the team which has faster dog walks will win the game, which essentially is at the moment. Okay, so it's actually 12 elliptical loci, actually. So, and these are adapted by so let me just show you the video. So this is the initial gate. So this is the pre-programmed, if you buy an IBO out of the box, this is how it walks. And you can see it's not that effective. And it's very sensitive to the particular texture of the carpet it's on, or grass and so forth. And so you can do much better by optimizing this. And now, this is what is learned after doing some number of iterations. You can't do that many iterations of this because it's so slow to actually run your IBO. You can imagine the training process is actually moving this thing, letting it run from side to side, maybe 10 times, and evaluating it each time, how long it takes, and then basically adjusting the parameters by gradient ascent to find a better policy. You can see it's much more effective if there's very nice policy.
To train it constantly, you know, like put a treadmill and be feeding the information from its speed and the parameters.
You could do something like that. Yes, and we'll come to methods which are better for sort of online training. The issue with most of these methods, you need to get all the way to the end of an episode to get some estimate of the return. I mean, you could divide it up into time periods, essentially on a treadmill. So they could do that. I think a treadmill is problematic because they really wanted to, because the texture is so important. they need it to be on the surface that they're playing on, is what they call that. Yeah.
So this was done by gradient descent or by
Finite difference gradient descent.
And so how does it work? So you let it run, and
Yeah.
you make one change to see if it's faster, and then this like will...
So-
how does it-
So you perturb the parameters a little bit in one dimension. You time the walk, then you go back. You perturb one of the other dimensions. You time the walk. You do that for all 12 of your dimensions. Then you find the gradient based on those 12 perturbations, which is going to move you uphill. You adjust the parameters uphill, and you
by some
repeat
step size.
by some step size, and you repeat. It's very naive, but it's quite effective here. And you can imagine that differentiating the I, because the IBO is this pre-programmed policy, people don't know it's gradient, and it's just some piece of code that's running this thing. You don't have, you don't necessarily know the gradient. Okay. But often we do know the gradient, in particular when we're working with policies that we've crafted ourselves. Then typically we can come up with nice forms, such as the Gaussian for the policy, and then we can train much more efficiently than this approach. So the rest of the lecture is going to deal with these more efficient approaches, procedures for gradient ascent, policy gradient training. And the big gain is going to be you don't need to do these n different evaluations, you just need one. So it's a bit more like the robot's on the treadmill, and at every step we get some example of how well it's doing, and we can immediately update the robot. It also means that for this previous approach, you sort of need to be able to unroll back in time. You need to say, what if I tried some different parameters from that state? And you can try adjust one of your other dimensions. And then you need to go back in time and say, well, what if I adjusted this other parameter? And again, we won't need to do that for all the methods. Okay. So to do this, we need to know analytically the policy gradient. If we have the analytical form for the policy gradient, we can do much better. So that's the goal. We're going to assume we have a differentiable policy whenever it actually picks an action that it's going to be differentiable, and that we know what that derivative is. In other words, we know the gradient or the gradient of the log of the policy equivalently. Okay, and what we're going to do is exploit this following trick. It's called the likelihood ratio trick. So what we're going to do is we're going to rewrite the gradient of the policy in the following way. So we're going to rewrite the gradient of the policy as the policy multiplied, so we're going to multiply and divide by the policy. Okay, and now we're going to note that this term here is actually the gradient of the log policy. Okay, so we've got the policy multiplied by the gradient of the log policy. This is called the likelihood ratio trick. And the reason it's useful is because now, if we want to sample our policy, we just take a sample of our policy. So if we want to look at the expectation of our policy, everything is multiplied by the probability with which we really pick actions. So we just need to look at this term here when we take expectations. So let's make that concrete. So if you're familiar with statistics or maximum likelihood training, you've probably come across the term the score function. So this term here is what we call the score function, this gradient of the log policy. And this is the sort of key things you need to know. So what does that score function look like? Well, let's get some intuition for that thing. So we're going to use two kind of common policies where this might be used. The first is a softmax policy. And the idea is we're going to take a linear combination of our features, just like we did in the last lecture, to get some kind of number representing how good is it, how much do you want to take this particular action. We're going to look at features of the state in action, and we're going to multiply those by some weights. That sort of tells us how much we prefer to take this action in this state. And then what we're going to do is just take the probability in proportion to the exponentiated value. So the probability that we pick a particular action is just proportional. So the log probability is proportional to this linear combination of features with weights. So the more we weight a particular feature, the more we'll choose to take that action when that feature occurs. Okay. So what happens when we use this particular form of policy? So if we take this particular form of policy, then what does the score function look like? It turns out, I won't bore you with the math, but it has this quite nice form, where it just turns out to be the feature minus the average feature. So it's whatever feature you actually picked minus the amount of the average over those features, over all the actions you might have taken. So that's the score function for the softmax. Now in continuous action spaces, I've argued we should be using something like a Gaussian as a reasonable choice. So we might choose something like a Gaussian with a mean given by some a linear combination of the state features. So this is now, we're sort of saying the action we'd like to pick, there's some features of state, and we're going to weight those features here. Well, again, it's the action you actually took minus your mean action, so how much more than normal you're taking this action, scaled by your variance. So in both cases, you get something, the score function can roughly be interpreted as sort of how much more than normal you're doing stuff. Where stuff here is your actions multiplied by features, and stuff before was your features of these state and action features. Okay, so there's a sort of intuitive interpretation of this term. It's like, has a nice form, it's how much more than usual you're doing stuff. And you can think of these as like our policy features. So this thing now, you can think of as features of the policy. So these things give you some useful information about the policy that we can use to represent stuff. Okay. So we're going to now use this likelihood ratio idea to come up with something called the policy gradient theorem, which tells us exactly the analytical form of this policy. But to do that, to keep the math simple, I'm going to consider a very simplified form of MDPs, which are basically one-step MDPs, where you basically start in some state, so you start in some random state, you get to pick one action, you get a reward, and then the episode terminates. So it's a very simple class of MDPs. So you start, your state is drawn from this distribution over states, and then you're going to get just some reward after that state. And so there's no consequences to what you do beyond getting that immediate reward. And the question is, how do we find the policy gradient in this simple setup? So what we do is use these likelihood ratios. So here what we care about, the objective function we're going to try and optimize here, is the expected reward under our policy. So we want to pick the policy that gives us the maximum expected reward under our policy. So what do we mean by that? Well, we mean if we average over all the states that we could start in, and we average over all the actions that we're going to pick in our policy, which might be a stochastic policy, remember, and we're going to get some reward corresponding to picking that state and that action, then that will be our objective function. Okay, that's the objective function we're trying to maximize. So we want to find the gradient of this thing. So the gradient of this thing, the only term here which depends on parameters theta is the policy itself here. Okay, and so we're just going to have the gradient of this thing here, which using our likelihood ratio trick, we can rewrite policy multiplied by the score function. That's the likelihood ratio trick that we just saw, which is just the expected value of the score function multiplied by the reward. Okay, so the policy gradient actually has this very clean form, which is if we want to follow the gradient of the policy, all we need to do is update our parameters in proportion to this score function, like how much more than usual stuff happened, multiplied by the reward that we saw when we picked that particular thing. So in the Gaussian case, it's like you pick an action, if you get more reward than usual, when you picked something, when you did that action more than usual, well, you should do that action more. That's what this is telling you. Okay. People, any questions here?
So that's the gradient of the log policy, and the R is outside the gradient, it's multiple.
Yes. Yeah, this is outside the gradient. So R doesn't depend on theta. So in the sense it doesn't matter. Okay. So it turns out that the same observation is true for the general MDP setting. So for multi-step MDPs, not just this one-step MDP. And all we need to do to generalize to the full case is we're going to replace the instantaneous reward that we had before with the long-term value, Q pi, the expected return that we would get. And now, for any of our objective functions that we had, this start state objective, the average reward objective, or the average value objective, we come up with this following fundamental theorem called the policy gradient theorem. Okay, so this is an important theorem to know about. It basically tells us that the gradient of our objective function with respect to the policy parameters is just the expected value. So now this expectation is now both over the states that we reach under that policy and also the actions that we pick under that policy. So it's an expectation in states and actions. Oh, sorry. And it's the expectation that the score function So now this really is outside the gradient. So this is a separate term to the gradient. So the gradient of the log policy, the score function, multiplied by the value function. So if you get, so we're just going to, at each step, the kind of algorithm we'll look at, well, let's actually go there. So there's a very well-known algorithm, which was originally called the reinforce algorithm, that you can think of as the Monte Carlo version of policy gradient algorithms, where we're just going to use this policy gradient theorem to give us a very simple algorithm to update our parameters directly by gradient descent without requiring any estimates of the value function. So how do we do that? We use the policy gradient theorem, and we use the return as an unbiased sample of our action value function. So remember that this thing is just the expected value of this. That's what the value function means. So we're going to use a stochastic gradient descent algorithm, where we just take a sample of this expectation, we're going to update in the direction of this whole thing here, replacing Q with V. Okay? So just going to move a little bit in the direction of the score function, how much more than usual our features occurred, or how much more than usual we're picking, how much bigger than usual our action is, multiplied by the return. So the algorithm would look something like this. So you'd run an episode, and then for each step in that episode, you would update parameters by the step size multiplied by the score function for that step, multiplied by the return starting from that step. Okay, and then you repeat and do another episode, update again. Okay. And then if you, so let's get some intuition for that. So imagine that we were using our softmax. So the softmax was the feature multiplied by the average feature. So this basically says if a feature occurs more than usual and we get a lot of reward, then you would like that feature to occur. You'd like to pick actions corresponding to that feature more. That feature is a good feature. That feature represents something you're happy about if you get a lot of reward when that feature is on more than usual. If the feature is on less than usual and you get a good reward, well, then you want to have less of that feature occurring. Having less of that feature is a good thing. So you reduce the parameter corresponding to that feature, and so forth. Yeah?
So why in the robot we can't parameterize the policy?
So you can come up with your own parameterization. I think the motivation for doing it there is there's just some black box piece of code representing the policy which doesn't have a nice form for which we know this term here. So it's just a black box, plug in your parameters and it does something. So you don't know whether it's being represented internally by there's no function inside that you can exploit. So you could come up with your own parameterization, plug that in some sense and do that. But there's a certain, for these black box settings, it's sometimes useful to know that finite difference trick. Okay, so here's a simple example where this is being used. So this is called the puck world. Basically what happens is you've got this, it's like an ice hockey game, and there's this puck sliding around, which probably made by Canadians, this paper, I should check. And there's this puck which slides around, and the puck is basically under, there's a little bit of control that can be exerted on this puck. It has a lot of momentum sliding along the ice. It can be perturbed in one direction or another a little bit at each time step. It has a lot of momentum. So you have to very slowly kind of craft its path into some curve towards the target. And then what happens is that this target, which is represented by the shape, it moves around every 30 seconds. It resets to a different random location. And so this puck has to find a way to sort of to move around. So it needs to speed up as much as it can, slow down before it gets there, and then slow down and stay as close as it can to the target before it jumps to somewhere new again. And if you run the policy gradient algorithm and look at the average reward per time step it gets, you get, this is very characteristic of policy gradient algorithms. You get this very smooth improvement. It's literally just following the gradient of the objective function, and this thing's very smoothly improving. I'm getting more and more reward until it's actually quite effective. Okay, this one I believe is a Gaussian policy in this case, linear Gaussian. And this was using a variant of that reinforce algorithm.
For instance, iterations there, what's that iterations of individual move?
Episodes.
The entire episode of the...
Yeah,
Just it's a huge number of iterations.
yeah, so it's slow.
Very
So that's
slow.
the lesson, actually. So the lesson is, look at that number there, that's big. These methods are slow, reinforce is slow. And so, which brings me nicely on to part 4. So we've come up with a nice gradient. We know the principle of how to follow this thing, but reinforce can be very, very slow to update. And we're going to talk about the reasons why and come up with ways to fix that so you get much more efficient algorithms, which are sort of the state of the art of what people do now. So, queuing me up nicely, what is the problem? Well, that Monte Carlo policy gradient that we looked at has very high variance. So we're looking at complete returns, and we're looking at this score function at every single step based on the randomness of our policy and the randomness of what the environment does at every single step, all the way to the end of our episode, which might be the randomness of where these locations jump about. All kinds of things can happen, and we end up with some return at the end of it. And is that return good or bad? Well, it's hard to say until you've seen an awful lot of episodes. Okay, so what we're going to do in this section is we're going to do something to really reduce the variance of that estimator. So the same approach, we're now going to use something called a critic. And what's a critic? A critic is something, you can imagine there's sort of two parts to the agent now. There's the actor. The actor is the thing which represents the policy that's taking the actions. It's acting, it's doing something, it's picking actions according to its policy. And then there's a critic, which is sort of sitting there, watching the actor, saying, hang on a minute, I don't think that was a good idea. And the critic is basically estimating the value function for the current policy that the actor's following. Okay? So you have this Q pi, and we're coming up with some critic that's estimating that Q pi. Okay. So to do that, we're going to need two sets of parameters. We need one set of parameters for the critic, and that's going to have some parameters to estimate. There shouldn't be a W here, by the way. This is just Q pi. There's just one set of parameters that's estimating the true value for that particular policy. That's the critic. And then there's an actor, which is going to have this parameters theta representing the policy. And what we're going to do now is, instead of updating these parameters in the direction of this true value function, we're going to simply update the parameters in the direction suggested by the critic. So the critic's going to be used to point the policy in the right direction. So what we're going to do then is we're going to take our policy gradient theorem that we had. So we had the policy gradient theorem before, where we had Q pi here, the real policy. And now all we're going to do is replace Q pi with our estimate, QW, just by substitution. We're going to say, well, okay, this is probably a reasonable approximation in many cases. And so now we're just going to update, just like reinforce, we're going to update a little bit in the direction of this. But now, instead of using just a sample of the return, we're going to use the critic. So this is much, much lower variance, because we're not looking at a complete return that we're getting from a whole episode. At every step, we can use the critic to separately estimate very efficiently what the value of that particular action would be in that particular state. And that gives us a much lower variance estimate. It's still too high variance. We can do better and better. There's several steps remaining to do better, by the way. But this is one big step that does much better than reinforce already. Okay, so what does the critic do? So the critic, we need a critic which basically solves this problem. We want our QW to look like Q pi. This isn't it. And that's a familiar problem. That's what we call policy evaluation. We saw that in the last lecture. We basically want to know how good is a particular policy, pi theta, the policy that's being followed by our actor, under the current parameters theta. And so we've looked at this in the last couple of lectures, and there's various ways you might solve this. For example, using Monte Carlo policy evaluation, using temporal difference learning, using TD lambda. You could also use some of the least squares methods we looked at the end of the last lecture to do this very efficiently. We're not going to look at least squares today, but you can apply least squares method to the critic of a act-critic method. And so it's really, the critic is known. There's nothing new to say about the critic. It's the problem that is the solution we've been using all along. So what we can do is come up with a very simple act-critic algorithm then. So let's say, just to fit in with our last lecture, we're going to use a linear value function approximation to represent the critic. So we're going to say QW is going to be linear in some parameters W, so a linear combination of some features of the state and action. And now we're just going to update the critic, for example, by linear TD, update those parameters, and we're going to update theta by this policy gradient we've looked at. And that gives us an algorithm which looks something like this, which basically says for every step we're going to sample from our, so for every step we're going to keep sampling from our policy, an action, and then each step we're going to look at the reward we got, take a new action, get the TD error, the reward plus our predicted next value minus the value that we thought we would get. And we're just going to update the critic parameters in the direction of the TD error. This is the linear TD algorithm that we had last lecture. So we're going to update the critic parameters a little bit in the direction of the error multiplied by the features. We're going to update the actor parameters in the direction of the policy gradient. So a little bit in the direction, so alpha and beta are just two different step sizes. They could be the same, they could be different. Now we're going to update a little bit in the direction of this score function, how much more than usual we pick those particular features, multiplied by the action value that's given to us by the critic. Yeah?
For this to work, does the policy need to be stochastic? If it's deterministic, it will just push the test.
Okay, so until recently, people would have perhaps answered that question by saying these algorithms are not defined for deterministic policies, because you have to, this term, it's not clear what this term means. Turns out that I'm writing a paper at the moment that says actually you can do it with deterministic policies. It has quite a nice form, but take about that separately, I think. It's, yeah. So new work says you can take the deterministic limit of this and you still have a well-defined policy gradient algorithm. It works really nicely. And it turns out to be similar to an existing class of algorithms that didn't have much theory before. So you can still do it, but that's not what people normally do. Okay, so we did this sort of naive thing so far, in a sense. We just said, we've got this approximately equal to here. And the question is, how bad is this approximation? So what we did was we just substituted the true policy with our estimated policy here. And the question is, can this make things go horribly wrong? You know, is this really anywhere close to this? Are we really going to be finding a reasonable solution once we're doing that? And so another way to put that is that we've introduced bias by approximating the policy gradient. The bias policy gradient might not find the right solution. So if we go back to one of our motivating examples where we had that aliased grid world example, and now we're using some aliased features, the same features that we struggled to represent the value function with before. You know, the greedy policy wasn't very good, remember? So now if our critic uses those same features, can we still solve that grid world example? You know, we should be asking questions like this. Is it reasonable, or have we kind of broken everything by using the same features for both the policy and the value function? And it turns out that if we do this in just the right way, then we can avoid introducing any bias at all. We can turn that approximately equals into an equals if we do things in the right way. So it can still follow the exact policy gradient even though we're using a critic in place of the true value function. And this should feel surprising. So how does it work? Well, there's this theory, it's called the compatible function approximation theorem, and it basically says if we pick our value function approximator to sort of match the policy representation we've got in just the right way, then everything will be compatible and these policy gradient algorithms will still work really nicely, even once we've got a critic there. So what does the compatibility really mean? Well, there's two requirements to make it compatible. The first requirement says, basically, that the representation of our value function sort of has to use the same features that our policy uses. And that's basically what this is saying. Saying the gradient with respect to the parameters of the value function has to be the same as the score function. So what would this look like in practice? This might basically means that, for example, this basically means that the action value function has to be linear in these things. So the action value function has to be linear in terms of these policy features for this to be satisfied. Now the second requirement is that the value function minimizes the mean squared error between QW and QPi. So in other words, it has to have this particular form, and the W that we find has to be the best W in terms of mean squared error. And if those two things are satisfied, then the policy gradient is actually exactly correct. There's no, our approximation's gone away here. It's exactly equal. There's no bias. Magic. Okay. So where does the magic come from? So I'll just spend 1 minute explaining this. It's actually very straightforward to understand. So remember, we have these two requirements. That this gradient of Q with respect to W has to be equal to our score function, has to minimize the mean squared error. So if we take the second requirement, well, to minimize the mean squared error, that basically means that the gradient with respect to W of the mean squared error has to be equal to 0 at the minimum for it to be a solution. Okay. Well, the gradient of the mean squared error with respect to W is just, by the chain rule, it's the error between W, so we have this, the gradient of the squared error is just the error multiplied by the gradient with respect to W of Q. Now, by the form of our compatible function approximation, the first component was that this had to be equal to this. That's the form that we insisted on for our compatibility. That the gradient of Q is represented by these four things. And so now we just collect terms together, and collect this term on the left-hand side and this term on the right-hand side. We basically get the expected value of this thing is equal to the expected value of this thing. And if you look at it, this is basically telling us this is the policy gradient from our policy gradient theorem. That, the policy gradient has to be equal to this sort of approximate policy gradient where we substituted Q pi with QW. Q theta should probably say Q pi, it's the same thing. So as a result of this theory, that means we can just substitute this in directly, and everything's very nice. Okay, so what does that really mean? It means that when we use our actor critic, if we pick our features to match up with the features of the policy, then the actor critic theory actually is completely reasonable. We're really still following the gradient. Nothing bad can happen to us. It all works nicely. Okay, so that was like the first trick for reducing variance. The second trick for reducing variance is called a baseline. So the idea of this is that so far, what we had is we're updating things in the direction of our score function multiplied by the action value function. So what's this is going to happen is sometimes, you can imagine you might be in a problem where all of your values are really high. So you run one episode, you get a value of, one step you get a value of 200, and the next step you get a value of 210, the third step you get 190. And because these are all very large, we keep just thinking, well, these look good, so it's very tempting to just keep moving your policy in the same direction. And it takes a long time for things to sort of equalize out. So what we can actually do is sort of normalize this policies by subtracting a baseline to bring it back down to, say, subtract 200 of all of those values. And it turns out that subtracting a baseline doesn't change the direction of the gradient. So all this is showing is that we can basically subtract any baseline function of state without changing the expectation. And the reason is that for any function of state, anything which isn't a function of the action, so this could be like some baseline just subtracting 200, or it could be something which depends on the particular state you're in, how much you subtract off. It turns out the expectation of the score function times this b thing, if you just write out this expectation, this is just using our policy gradient thing, this gradient pushes outside the expectation, the b pushes outside this expectation as well, and basically this thing just sums up to 1, because this is the probability. And so the gradient of 1 of 0. Okay? So that means we can subtract off anything like this, any term like this from our policy gradient without affecting the result. So what do we choose? Well, it turns out a very good idea for the baseline is the state value function. So in other words, we're going to basically say what we're going to do is replace our what we had Q pi here before, we're going to replace it with something called the advantage function, which is the value you get for taking action A from state S minus the value you would expect just from being in state S under your policy. So how good is action A compared to how good is it on average to be in state S? So we're normalizing everything. We're just sort of normalizing by how good on average it is to be in a particular state. And so if we replace Q by A, then we get a much more efficient algorithm. So that's our second trick. So we've got 2 tricks for reducing the variance. The problem is that Q, we saw in the last lecture how to estimate Q. What we didn't see in the last lecture is how to estimate A. So how can we actually estimate the advantage function? Well, here's 2 ways to do it. So we need a critic that's going to estimate the advantage function now. The simplest way is to estimate both Q and V, and then just subtract one from the other. Okay? So if we estimate the state value function, we estimate the action value function, we subtract one from the other, we plug that in, and we're good to go. So you could, for example, imagine doing both of these by TD learning. Come up with an estimate of Q and an estimate of V. The disadvantage is we end up with a whole new set of parameters here. So we've got 3 sets of parameters now, one for the policy, one for the action value function, one for the state value function. So here's a second way to estimate the advantage function. So it turns out that for the true value function, v pi, let's look at the TD error. Okay? So the TD error for the true value function is the reward plus the value function from the next state, the true value function from the next state, minus the value function of the state we were in. That's the TD error. So in expectation, if we take the expectation of this thing, conditional on particular state in action, so what's the expected TD error? Well, the expected TD error is just the expected value of r plus gamma v minus v, which is basically the action value function minus the state value function, which is the advantage function. So the TD error is an unbiased estimate of the advantage function. So you look at one TD error and it's sort of telling you how much better than usual was it to take that action that I took. That's kind of one way to interpret the TD error. Like I took an action, I ended up somewhere that did better than I thought. So now that's an estimate of the advantage function. So what we can actually do is take our policy gradient theorem, and this is sort of the one last way we can plug this idea in. So instead of using either so we started off with the action value function here, we replaced that with the advantage function. Finally, we can also replace it with the TD error. Now in practice, we don't have the true value function, but we can do the same idea just by keeping a state value function. So we're back to 2 sets of parameters. For this algorithm, you don't need an action value function. You just need a state value function. You use the state value function to estimate your TD error. You plug that into your policy gradient theorem, and you get an update direction. So just based on the TD errors. So if in one particular state, if the action you took did better than you thought, your TD error will be high, and then you update in proportion to the score function multiplied by that TD error. And you do that at every single step.
So you don't have to estimate QSA at all?
No. No. So Q is gone in this algorithm. Okay. So I'm going to skip this part. This is the part I'm going to skip. So summary of the part I'm skipping, you can do TD lambda for the critic. Turns out you can also do something like TD lambda for the actor as well. It's on the slides if you're interested. Won't be in the exam, I'm skipping it. Okay. All right. So finally, in the last 4 minutes, it turns out that when you're doing gradient ascent, you don't have to follow the vanilla gradient. You can follow any direction of ascent, even if it's not the gradient itself. So you can take any vector which has a positive dot product with the vanilla gradient, and it will still take you towards a maximum. You don't have to follow the actual gradient itself. As long as you're going uphill, you will make progress. Now it turns out that some ascent directions are better than the vanilla gradient. How can that be? Well, it can actually get you there much faster. And I'll just show you a picture to make this clear. So here's this is actually for some controller problem, a real sort of engineering problem. You get some policy gradient. So this is the objective function for the policy that's being plotted here with a 2-dimensional parameters to the policy, and this is the vanilla gradient for this policy. And what you see is that it's got these very flat lines. The gradient is very insensitive to what's going on in this flat region. What we do is reparameterize this in a particular way, follow something better. We want to get there much faster towards the optimum. Now, one particular way to do this is called the natural policy gradient, and it has a particular property which basically means that it's completely insensitive to reparameterizations of the policy. So all it cares about is the actual probabilities that your policy has. It doesn't care how those are parameterized. So even if you reparameterize the policy in a different way, if it had the same probabilities, the problem is it would change the vanilla gradient, but the natural policy gradient is going to be invariant to those reparameterizations. And so what it means is it actually means that if you were to follow, if you could choose, consider all the ways that you might change your policy by just some small amount, where by some small amount we might mean just a little tiny bit of KL divergence from your original policy. So you limit the amount that you can change your policy by a tiny bit, and then ask what's the best you can do whilst only changing by a small amount. And it turns out that that is what the natural gradient means. So the natural gradient is a good thing to know about. It has this particular form, where all you need to do is take your gradient direction that you had before and multiply by something called inverse of the Fisher information matrix. And this thing is basically, it's like, it's the second order version of the score function. So it's the score function multiplied by, so it's the outer product of the score function with itself, or the Hessian of the score function. Derivative of the score function. Okay. So all I wanted to show you is there's this very neat trick, but it turns out that the natural gradient is actually even simpler than the vanilla gradient to compute when you use these policy gradient methods. And the reason is you get this very nice simplification. So using compatible function approximation, remember we have this property here. And all we're going to do is take our original policy gradient, we're going to take our A or our Q, doesn't matter which one you use, and you plug in our compatible function approximation here. Remember we were representing it by a linear combination of the score function with some parameters. That was our compatibility requirement. And it turns out that if you pull W outside of this, you end up with the Fisher information matrix multiplied by W. So the natural gradient actually is just W. In other words, if you find the compatible function approximator and you solve for the mean squared error and you find exactly the right W, and you want to follow the natural gradient, all you do is you update your parameters a little bit in the direction of W. So you've already done all the work you need just in the critic. You don't need to do anything clever in your actor other than move a little bit in the direction the critic says. So you solve your critic, and then you just update the parameters a little bit in the direction of W. Okay. So that's it. It does a lot better, and there's a cool example where you can solve a snake in a maze kind of problem using natural language critic. That's it. Okay. Question?
Is that like Newton method? Is that similar to Newton?
It's like a stochastic, you can think of it as this, because it's a stochastic policy, yeah.